So, a short exercise on manipulating trigonometrical expressions. Most of them will be done just by using sine squared plus cos squared equals 1, although some of them will have the double angle formula or the addition formula in it. Now, this question sheet will appear before each of the solutions to these 8 questions, so the way to do this would be to pause on the question sheet, attempt the questions, and then play the following short video to confirm you've got it correct or to see how it's done. First one, quick one. Looking at that suggests difference of 2 squares, but there's a cos squared there, so we'll probably take it a common factor. Anyway, start formally. Demonstrating the two sides are equal. Start with the left hand side, rearrange it until it comes out with the right hand side. So for the left hand side, I'll just rewrite it. It's cos squared theta minus cos to the 4th theta. We'll take out that cos squared theta as a common factor, leaving 1 minus, jumping the gun there, 1 minus cos squared theta. And then of course, 1 minus cos squared, remembering sine squared plus cos squared is 1, just makes sine squared. Put it back into that order so it looks exactly the same as it. Sine squared, cos squared equals right hand side. That's that we've done. Right, now question 4.2. Next one. Here's a polynomial in cos theta, various powers of cos theta. It's also a quadratic, but the discriminant, that's 9, take out that's negative, so it's not going to factorise, so that's not going to lead towards it. So I'll just go through the whole lot. I don't want any cos's, I want sines. So every cos squared will be 1 minus sine squared, and that's just it squared again. So 1 minus sine squared theta squared plus 3 times 1 minus sine squared theta plus 5. So that's going to be 1 minus 2 sine theta, sine squared theta, plus sine to the 4 theta, plus 3 minus 3 sine squared theta plus 5. And then just gather it up in the order of the powers. So we've got sine to the 4 first, sine to the 4 theta, minus 5 sine squared theta, 139, plus 9. And that's all there was to that one. Now question 4.3. 4.3. Show that tan squared minus sine squared is tan squared times sine squared. Sounds a bit odd as an identity. Well, let's see. It's an identity, so start off with the left hand side. So left hand side is tan squared theta minus sine squared theta. Right, now there's still tan squares mentioned there, but not any obvious common factors. Probably better to take this into the other form of sine over cos minus sine squared theta. Now the next thing we suggest would be, well, I could possibly have a common factor there. What I'll do is I'll add it to a single fraction first. So making it all out of cos squared theta, I'm going to have, that's got it all, so that's sine squared theta, get back, minus, that doesn't have it, so that'll be minus sine squared theta cos squared theta. Then I could take out the sine squared. Sine squared theta times 1 minus cos squared theta, all over cos squared theta. Taking out the common factor. That's the simple identity. Sine squared plus cos squared makes 1, so rearranged. That says you've got sine squared theta times sine squared theta over cos squared theta. But looking at the answer, I think I'll put it over this part, cos squared theta. So that part comes to tan squared theta times sine squared theta, which is the right hand side. And question 4.4. 4.4 now. This time using that reciprocal of cosine, the second sec. So here's a polynomial in sec. You have to rearrange it into a polynomial in tan. Well, you've got the same connection. The connection you had with sine squared plus cos squared equals 1. If you divide everything by cos squared, then that's going to make tan squared plus 1 equals sec squared. Which is why you can use that substitution, of course, in integration. when you see something with 1 plus x squared, you can put a tan squared, and that'll then give you a sec squared. Still, using that substitution here. So, the first one, well, sec squared. So if tan plus 1 equals sec squared, then sec squared is 1 plus tan squared. And that's sec squared again. Minus 3 times sec squared is 1 plus tan squared. I'll have to get rid of this. And then plus 1. So what's that all together? Maybe I should have put that first. No, it doesn't matter. 1 plus 2 tan squared plus square that squared and make it a power 4 minus 3 tan squared plus 1. Put the higher powers first. Tan to the 4th theta minus tan squared theta. Numbers 2 take away 3 minus 1. That's that one done. Question 4.5. Next one, back to an identity again. Cosines and sines to show a cot. Well, certainly a cot would be that, and that's tan. But probably with this one, the best thing to do would be to make that into a single fraction, because that's a single term. So start off, left hand side equals, oh, I have to write it again. I'll not write it again because it's long this time. I'll just add them up. Common denominator would be sine theta cos theta. So that's got the sine theta, it'll need to be multiplied by cos theta. So cos 3 theta cos theta. Sine 3 theta. That's got the cos theta, they both need to get multiplied by sine theta. Sine theta. Then you look at that and you can see a couple of patterns. The top of it is an expansion. It's an expansion of cos A minus B. The bottom's almost the sine 2 theta 1. So the top can go back to cos of 3 theta minus theta. And the bottom is half of 2 sine theta cos theta. So the top then just becomes cos 2 theta, and that becomes half of sine 2 theta. That's 1 over, that's a half at the bottom, so that would become 2 over 1, so 2 times the top. And that's just 2 times, that's the upside down, the reciprocal of tan. So 2 cot 2 theta, whoop, as required, equals right hand side. Right, question 4.6. This time it's got coseconds, it's got inverse sine here. Now there is a pattern, just the same as with sec and tan for cosec and cot, just by rearranging sine squared plus cos squared equals 1. I can make one with cots and cosecs just by dividing everything by sine squared. So I've got 1 plus cot squared equals cosec squared. But that's not what's going to apply here because I've got these double angles. Simplest thing here would just be to rewrite them the way that they are. So for the left hand side, I'll just write it out, it's not so long this time. Cosec 2 theta plus cot 2 theta. What can we do? Well, that certainly means 1 over sine 2 theta, and cot means the reciprocal, which would be cos 2 theta over sine 2 theta. Well, that's handy, they've got the same denominator. So over sine 2 theta, I've got 1 plus cos 2 theta. Then I'll start to think, right, multiply them out because I want them to be single angles. Well, that's only got the one option. 2 sine theta cos theta, 1 plus. Now, cos 2 theta, that could be 2 cos squared minus 1, or 1 minus 2 sine squared. Well, I fancy the 2 cos squared minus 1 because the 1 will knock out the 1 and there's no extra 1s floating about. So I'll go for that. So we'll go for cos 2 theta is 2 cos squared theta minus 1. So now I've got this, we'll just spell that one out. So I've got 2 cos squared theta, can I just write that, cos theta, over 2 sine theta, cos theta. And then these parts cancel out, leaving cos over sine, which is cot theta, which is the right hand side. Question 4.7. 4.7 looks much like the last one. Double angles, single angles. Well, spell it out then. So left hand side equals, I'll just write it out, 1 minus cos 2 theta over sine 2 theta. So sine 2 theta to sine theta cos theta, aiming for single angles. 1 minus, now this time since it's 1 minus, at the two forms I could have 2 cos squared minus 1, that'd be minus minus, that'd give me a 2, or better than that, 1 minus 2 sine squared theta. So I've got 1 minus 1 minus minus, so that's 2 sine squared, which I think I'll just write as 2 sine sine to match the bottom. Over 2 sine cos, out you go, leaving a nice clean tan theta. Well, that was especially easy. 1 to go. And the last one, 4.8. Well, this is a much longer question. And so, the last of these questions involving these trig identities. Given that, show that the tangent of these two angles, alpha and beta, comes to 1. Now this harks back to the days when we used to have more of these formulae in the highers. So the first part would be this. If alpha was the inverse tan of a half, that means that tan alpha is a half. And if beta was the inverse tan of a third, then the tangent of beta is going to be a third. And if you're going to find the tangent of alpha plus beta, then you're going to be involved in some sort of expansion. Now there was an expansion for that. However, nowadays, here anyway, with the highers, that's gone, and you're meant to do it via sine alpha plus beta over cos alpha plus beta. But I'm just going to take this right back to that expansion the way it used to be. So what is that for the sine alpha plus beta? That would be sine alpha cos beta plus cos alpha sine beta over cos alpha cos beta minus sine alpha sine beta. Now you could evaluate that now by taking these two in that similar fashion of reconstructing the triangles, so that if the tangent of the angle alpha is a half, that means that makes a half. And then you could find the length of that side, 1 and 4 is 5, that would be root 5. And then I could start filling in all the alpha ones here with 1 over root 5s and 2 over root 5s. But I'm not going to. I'm going to carry on and resurrect, dig up this formula for the expansion of tan alpha plus beta, which is done quite simply by this. If I want to generate tans, separate tans from this, from these sines and cosines, then I'm going to divide. You see straight away there, sine over cos, sine, sine. If I divide everything by cos alpha, cos beta, I'd have this. Sine alpha, cos beta over cos alpha, cos beta, plus cos alpha, sine beta over cos alpha, cos beta. So it's going to become a chant soon, isn't it? Over. Each of the 4 parts is getting divided. Must do the same to the top and the bottom. Every term on top and every term on the bottom of a fraction. Cos alpha, cos beta, divided by cos alpha, cos beta, minus sine alpha, sine beta, divided by cos alpha, cos beta. And then lots of bits will cancel out. So the cos betas will cancel out there, the cos alphas will there, the whole lot there, and in this one nothing cancels out. And that eventually leaves me with, I've got tan alpha, such a simple result, tan beta. See that? Tan alpha plus beta turns out to be tan alpha plus tan beta, but divided by, that just cancels to 1, minus tan alpha tan beta. And I'll just take that up here to evaluate it. So if that's equal to that, then I can put these figures in. It's going to be a half plus a third over 1 minus a half times a third. And of these root 5s and so on. A fraction with fractions, multiply everything by whatever they're all going to, 6, so 6 times everything. 3 plus 2 over 1 minus a sixth, 6 minus 1, 5 over 5, 1 as required.